Calculus, here we are in section 3.8. It is the last section of this chapter, so we're going to be preparing for a test, and we're going to be talking about direct, inverse, and joint variation. Though I don't usually do this, I have some typed up or some printed out vocabulary phrases for us, so it will be a little bit easier for you guys to see. But we're going to be talking about this concept of variation. And basically what variation is it's giving us a relationship between two variables, x and y. And so direct variation means that y is proportional to x. So y is equal to k times x. Or we can honestly think about it as y over x is equal to some value k, meaning anytime I'm dealing with this relationship of y terms and x terms, it's going to have a constant relationship k. And that kind of comes down to the idea of constant variation. So constant variation, or constant of variation, let me say that correctly, refers to this constant that is the ratio in this case, and we'll see how it plays out in these other types of variation. So direct variation is when y is equal to k times x, or we can write it as y to x is equal to some k. Here's what I want you to also realize is y doesn't always vary directly with x. Y could vary directly with x to the n power. As long as n is greater than 0, k is called the constant of variation, and you see that there. So that takes care of both of these. Let's go ahead and look at the concept of inverse proportionality. We have inverse proportionality when y is equal to k divided by x, or x is dividing k. So remember, before we had x multiplying k, here y is dividing x multiplying with k, here x is dividing k. And what we want to realize is that the relationship could also be written as y times x is equal to some number k, meaning the product of the two values, y and x, will always be a constant value. And again, just like last time, we realized that x doesn't have to be to the first power. It could be to any power in order for y to vary inversely as x to the n. Again, as long as n is greater than 0. And finally, we have the concept of joint variation. And joint variation is generally just a direct variation situation where you have more than one variable. You notice that the x to the nth power and the z to the nth power are varying directly with y. So joint variation just means that we have more than one thing going on. And so that takes care of our vocabulary and brings us right on into our examples. Example 1, suppose that y varies directly as x and y is equal to 27 when x is equal to 6. So we remember what direct variation is. It's y is equal to, and since it varies directly as x, we're talking about just x, k times x, y is equal to k times x, or we can look at it as y over x is constantly going to be equal to some k, as long as we're talking about this relationship. So whichever way you like it, some students really like to set it up as a proportion when we set two ratios equal to one another. So we could have 27 is to 6 is equal to, and says find the constant of variation and write an equation in this particular form. So we want to find out what that constant of variation is in part A, and we would do that by simply simplifying this expression. And so 27 over 6 can be reduced to 9 over 2, 9 halves, and so the constant of variation is 9 halves, or 4.5. I think I prefer the fraction, actually. All right, so that would be the constant of variation, and then B asks us to use the equation to find the value of y when x is 10. So a couple things we can do. Now that we know what k is, we can simply plug in, we're looking for y when x is 10, so y is equal to 4.5 times 10, which gives us y equals 45, right? However, we could also just, if we had this problem, we can start off with 27 over 6 and say that that is equal to, remember, it's y is to x, as y is to x. In this case, it's 10. So you get yourself a proportion where you're cross multiplying, and you know that this would be 270 is equal to 6y. And then if I divide both sides by 6, you see we would end up with the same thing, that 45. So I just want you guys to see that there's a couple of different ways to approach the problem. Hopefully that's making sense. 6 goes into that. 4 times 24, you get a 3, and there's your 5. All right, boom. So that's what we have for that one. So that's example 1. In example 2, we're talking about auto safety. And so we're referring to the application at the beginning of the lesson. The NHTSA reports an average braking distance of 227 feet for a car traveling at a rate of 60 miles per hour with a total stopping distance of 359 feet. So we're going to take this information and the information at the beginning of the chapter. And here we added in some information about what we had at the beginning of the chapter. So you can see that the faster you drive, the more time and distance you need to stop safely, and the less time you have to react. The stopping distance for a vehicle is the sum of the reaction distance, which is how far the car will travel before you hit the brakes, and the braking distance, d sub 2, how far the car travels once the brakes are applied. According to the National Highway Traffic Safety Administration, under the best conditions, the reaction time of most drivers is about 1.5 seconds. Once brakes are applied, the braking distance varies directly as the square of the car's speed. So that's good information, and we're going to need it to answer our question. So if we go back to our problem here, the NHTSA reports an average braking distance of 227 feet for a car traveling 60 miles per hour with a total stopping distance of 359 feet. Okay, so now we've got some good information. We're going to write an equation of direct variation relating the braking distance to the car speed, then graph the equation. So the first thing we want to do is just establish the fact that the braking distance, which we saw referred to as d sub 2 here, will be equal to some constant k times the speed squared. So that's like the standard situation that we were given from this bottom part of the information at the beginning of the chapter. Now we want to figure out what that constant is. So in order to figure out the constant, let's solve for k. K is going to be equal to d sub 2 over s squared, and d sub 2 in this case, the braking distance is 227 feet, and the speed is 60 miles per hour. So we're going to square that. I'm going to get a calculator and do that real quick. We get approximately 0.063. Therefore, the equation that we're talking about, that speed is going to be equal to, or that braking distance rather, is going to be equal to 0.063 times the speed squared. So this is our equation. Let's go ahead and graph that. So I traded out the variables that we would ordinarily use, or that we'd want to use, d and s, or d sub 2 and s squared, to y and x squared. And then so now we can look at this graph on Desmos, which makes my life a lot easier. And we can think about, well, what does x refer to? So x is going to refer to the speed. So these values are not really all that great. So let's go ahead and get a better looking screen. I'm going to go over here to the wrench and change this. So we're thinking about speeds all the way up to at least 60 miles per hour. Let's go further than that. Let's go to up 100 miles per hour. So we can see we've got this little half of the parabola there, and our y values, maybe we could go from 0 to, or I like to go actually to -2, so I can see a little bit more clearly, all the way up to, well, our y values were going to be our distance. So those need to be pretty big, right? Like the one that we started off with 227. So I'm thinking, like, I'm just going to throw a 500 in there. Maybe that could be a possibility, just so I can get as much information as I can. So hopefully, okay, there we go. So hopefully you guys can see this part of the graph really is what matters, because we don't really have negative speeds. So if we're thinking about the domain of the situation, we want to be talking about 0 on up. All right, so here's our graph. Okay, so I stuck that graph right there over here in the corner. And now let's go ahead and answer some of those other questions. So the next part B, asks us to use the equation that we've created here to find the braking distance required for a car traveling 70 miles per hour. So that will require us to, looking for d sub 2, which is the braking distance, we're going to plug in the value 70 for the speed, and we're going to square it using a calculator. We get a distance of about 309 feet as the braking distance there. So that's part B. And finally, part C, I'll answer down here. Calculate the total stopping distance required for a car traveling 70 miles per hour. So we were given the total stopping distance. The stopping distance for a vehicle is the sum of the reaction distance, D1, and how far the car travels before you hit the brakes. So this total stopping distance is going to require the value from part B, which is 309 feet. And any idea how we will calculate this beginning part? How do we calculate the stopping distance? The first part, the reaction distance, d sub 1. So this is d sub 2 plus d sub 1 is what we need here for part C. And d sub 1 can be calculated given this bit of information. So we have 1.5 seconds is going to be the time it takes for the driver in general to make the decision to stop and then actually stop, actually push the brakes. So what we'll do is we'll calculate that distance given that 1.5 second, I guess, pause. So we have to keep in mind something. To find that D1, which is distance, we have to remember that distance is equal to rate times time, or speed times time. So we know that the speed is going to be 70 miles per hour, and we know that the time is going to be 1.5 seconds. And I hope right now you are thinking, this is not making sense. And the reason why is because you're dealing with miles per hour and we're looking at seconds, and honestly we want this answer in feet. So there's a whole lot that we're going to do. Well, maybe not a whole lot, but we're going to do some conversion factors to get the answer that we want. So first of all, let's start off with our 70 miles per hour, and we know that we want this in feet. So we're going to start off by changing our miles to feet. And in order to do that, we need to know how many feet will be in 1 mile. And if you don't remember it, it's like 5,280 feet are in a mile. So I'm going to put 5,280 over 1 mile. And so you can see my conversion factors. My miles will cross out. Once I do the multiplication, I'll be in feet. And now I'm going to change my hour to seconds, because that's going to be the rate that I need to deal with this situation here. And so in order to do that, I'm going to take my time. I'm going to start off and saying, okay, I know that 60 minutes. Well, yeah, I'm going to do it the other way, actually. I am going to get rid of the hours. I want minutes at the bottom, and then I'm going to change my minutes to seconds. So 1 hour is the same as 60 minutes. So technically, guys, I'm just multiplying by ones here, right? I'm not actually changing the value, but I am changing the units by multiplying by these little fancy ones, because 1 hour and 60 minutes is the same thing. So having the same thing over the same thing as a fraction is just 1. So I've got 1 hour, 60 minutes. That's going to change my hours to now minutes down here. And now I'm going to change my minutes to seconds. And so I know that I'll do that by saying that 1 minute is the same as 60 seconds. And so now when I do this, when I multiply all of this through, I'm going to grab a calculator and do it. When I multiply that, I will now have the speed in terms of feet per second. So that leaves me with 103 feet per second, just about. And so now I'm almost there, guys. I'm looking for the distance. Don't forget what we started fighting for. I had to change my speed to feet per second. And so now I can multiply 103 times, well, let me write it up here. So d sub 1 is equal to new rate, new way of looking at the speed of 103 feet per second, which is an equivalent speed, just looking at it in different units. And I'm going to multiply that by 1.5, grab a calculator so I can figure that answer out. And I get about 155 feet. So that's going to be that distance, just the distance of me deciding that I want to stop and actually put my foot on the brakes. I'm going to travel about 155 feet, and then I'm going to add that 155 to the 309, and I'm going to get something like 464. So the answer to part C, which was to calculate the total stopping distance, is 464 feet. Here in example 3, we're going to be talking about y varying directly as the cube of x, and y being a value and x being a value, and we'll see how this works out. So we've got direct variation. Y varies directly as the cube of x, so we know we can write it like that, and we can also think of it as y over x cubed is equal to k. So that hopefully will be helpful as we take a look at this. Y is equal to negative 67.5, so I'm going to do that. And when x is equal to 3, so that's 3 to the third power, and we're going to find x, or x to the third power. We want to find x when y is equal to negative 540. And so with this, I feel like we can do it, right? We're just going to take that 3 to the third power, which is 27, multiply it by negative 540. Let me write the number correctly. And then we're going to divide that by negative 67.5. And what we're going to end up with is x cubed. So let's go figure out what that is. So when we calculate this, we get 216. So x cubed is equal to 216. We got to figure out what x is, my friends. So we've got to take the cube root, just throwing little old-fashioned symbols back in there, get the cube root of that x cubed. And so what I do to one side, I do to the other, and then I get that x is equal to, well, the cube root of 216 is 6. So in that case, x is equal to 6. Let me roll back so you can see what the problem was. Maybe I can even shrink it so you can see the whole thing at the same time. All right, so that's example 3. So here in example 4, we have an inverse relationship. We see y varies inversely as x, and let's remember what that is. That means y is equal to k divided by x, or we can look at it as y times x is equal to k. So if y varies inversely as x when y is 21 and x is going to be 15, right? That's what we've been given here. Find x when y is 12. So find x when y is equal to 12. So we know that's still going to equal k, right? So when x is equal to, when y is equal to 12, and we're in the same situation, x is still going to be equal to k. So watch this. They're both equal to k. I was going to just like use my handy moving tool, but I guess I could just rewrite it. So 21 times 15 is equal to 12 times x. And guys, I think we can probably do some pretty good math without actually doing a whole lot of big time multiplication. I can divide 3 out of both sides, right? And so I get 7 times 15 is equal to 4x. And I don't know, I'm trying to do this right now. 7 times 15, I guess I'm going to have to do that. 5, 3, 7, 8, 9, 10. So we get 105 is equal to 4x, and divide both sides by 4. And x is therefore equal to 20 something. What is that? 25, 20, 6 1/4. All right, I did all that in my head. I should have just went and snuck the answer somewhere. Anyway, well, x is equal to 26 1/4. And so that's what we get. So what I want you to notice is that here, we didn't even stop to figure out what k was. And sometimes we don't. We didn't do that in the last example. We just used a relationship that we were given and made an equivalent relationship so we could solve the problem. Okay, so example 5 is our final example, and we've got a little geometry problem. It says that the volume of a cone varies jointly as the height h and the square of the radius r of the base. So when we know things vary jointly, let's just go back and remember what that is. Y varied jointly, meaning we had two variables that y was varying with, in a sense. See, here we have y varies jointly with x and z. So this situation is kind of what we should have in our mind. Let's go ahead and see how we can apply that to the problem at hand. The volume of the cone varies jointly as the height and the square of the radius. So we have some k times the height and times the square of the radius. So that's a joint variation situation of the base. Okay, find the equation of the volume of the cone with the height of 6 and the diameter of 10 centimeters. So we know we want the radius. Diameter is 10, therefore the radius has to be 5. So we're talking about 5 squared. And that has a volume of 50 pi cubic centimeters. All right. So I put this down here and I've got my k value. So we need to go ahead and solve for k. A couple things that we can do. We've got that 50 over here. This is going to be 25. And when I divide both sides by 25, I get 2 pi is equal to k times 6. I'm going to divide both sides by 6, and then I'm going to get that k is actually equal to 1/3 pi. And so now I can find, what did they ask me to find? Find the volume of a cone. Find the volume if this information is true. So the volume would be 1/3 pi times hr squared. So that's the formula. And that's it for our lesson. I hope it made sense. I hope that you can keep these different types of variations straight. And I look forward to talking to you soon. Take care.